In this video, we will prove the Grownwall's inequality in ordinary differential equation. This inequality uses frequently in ordinary differential equation. So, we will prove this one. The inequality says that for any non-negative constant m, if u and v are real valued non-negative continuous function such that this condition satisfies, then we can write ut as ut less or equals to m times e to the power integration of t0 to t v of s d of s. Okay. So, we will prove this one. Now, here there will be two different cases. First case, if m is more than 0, and second case if m is equals to 0. So, we will consider both cases. So, case 1. So, case 1 is if m is more than 0. So, if m is more than 0. If m is more than 0, then for so t is between t0 to capital T. So, if we consider h, where h is between t0 to capital T, then this equation 1 can be written as, then equation 1 can be written as follows. So, if we divide ut by whole of those, so we can write ut divided by, not ut, it is actually uh, because now we consider h. So, uh and m plus t0 to h, because we replace t by h, u of s v of s ds. So, this one would be less or equals to 1. Okay. So, I divide both sides by this quantity. Now, what we can do, we can integrate, okay, multiply both sides, multiply both sides by v of h, and integrate from t0 to t, and integrate from t0 to t. So, we will multiply both sides by v of h. So, u of h times v of h divided by m times, so m plus integration of t0 to h u of s v of s ds, and we will integrate from t0 to t, from t0 to t dh, or h varies from t0 to t, h varies from t0 to t. We are considering a small t. So, this would be less or equals to t0 to t v of h dh, where t0 less than or equals to t. Okay. Now, we know from calculus that if we take differentiate of denominator and if we get numerator, and if we integrate that one, then you will get natural logarithm of the denominator. That means the formula is this one, like integration of f prime of x, f of x dx. So if you integrate f of x, a function, and you get denominator, then it is in natural logarithm of f of x. Okay. For example, if you integrate 1 over x square and twice x, so you take derivative of this one, then you will get this one, the numerator twice x. If you take derivative of x square, you will get twice x. So if you integrate this one, you will get natural logarithm of x square. So if we take derivative of denominator, so if we take derivative, it would be 0, and if you take derivative of this one, then by second fundamental theorem of calculus, it would be u of h v of h, the numerator. If you take derivative of this one by second fundamental theorem of calculus, it would be u of h v of h. Okay. So if we take derivative, sorry, if we take integrate of this one, so it would be natural logarithm of the denominator. So we can write this one as natural logarithm of the denominator m plus t0 to t, t0 to h actually, u of s v of s ds, and this one varies from t0 to t, and right side would be same. Right side we have integration of t0 to t v of h dh. So if you plug t now, it would be natural logarithm of m plus t0 to t u of s v of s ds minus actually we can give another parenthesis here. Okay. So first we will plug t and then t0. Now if you plug t0 here, then lower limit is t0, upper limit also t0. So if you integrate this one, it would be 0. So we will have only natural logarithm of m. So ln of m. This is t0 to t v of h dh. Now we know natural logarithm a minus ln of b equals to ln of a divided by b. So that means ln of a minus ln of b equals to ln of a divided by b. Okay. So ln of this one minus that one would be natural logarithm of m plus t0 to t u of s v of s ds divided by m. So this one less or equals to t0 to t v of h dh, right? Now if you take this logarithm right side, then it would be e to the power. Okay. So m plus t0 to t u of s vs ds divided by m would be less or equals to e to the power t0 to t v of h dh, right? That means you can write this one as m plus t0 to t u of s v of s ds less or equals to m times exponential of t0 to t. Now we can, since this h is a dummy variable, we can write it is as s, so d of s. Okay. Now since in one ut is less than that one, Okay. So ut is less than that one. So if you compare this one with 1, then this one is less than or equals to ut, right? So this is less or equals to ut. So we can write, since in 1 ut is less or equals to, so ut is less or equals to m plus t0 to t u of s v of s ds, we have from above as u of t less or equals to, so u of t would be less than that one, m times exponential of t0 to t v of s ds. So this what we need to prove, u of t less or equals to m times exponential of t0 to t v of s ds, where t0 less or equals to t. So we prove for m more than 0. Now we also need to prove when m equals to 0. So that would be case 2. So case 2 when m equals to 0. Now if m equals to 0, then from 1 and 2, so if m equals to 0 here, so ut would be less or equals to, this is 0, that one, and here ut would be less or equals to, if m is 0, so less or equals to 0. Okay. So if m equals to 0, from 1 it would be ut less or equals to integration of t0 to t u of s v s ds, and from 2 we have ut less than 0. That means when ut is this one, then we need to prove ut less or equals to 0. Now for any number m mod or equals to 1, for any positive number, we have ut less or equals to 1 over m plus integration of t0 to t u of s v of s ds. Since ut less than that quantity, that means this is bigger, so if we add any positive number with this one, still it would be bigger. Since m is a positive number, 1 over m also positive number, so if we add 1 over m with the right side, still this side would be bigger. Okay. Now if you compare this one with the case 1, okay, if you consider this one with case 1, then we can write ut less or equals to 1 over m times exponential of t0 to t v of s ds, where t0 less or equals to t less than capital T. So we wrote it by case 1. Okay, by case 1. Now if we fixed t, and if m approaches positive infinity, then this would be 1 over infinity, it will approach to 0. So Thus, for any fixed t which is in t0 to capital T, t0 to capital T, this is parenthesis, this is square bracket, we can let m approaches positive infinity to conclude that so if this one approaches infinity, then ut less or equals to 0, so this completes the proof, because we need to prove when m is 0, then this is the case, and we need to prove ut less or equals to 0. So we prove ut less or equals to 0. So we prove for both cases when m is more than 0 and when m is equals to 0. So that's it for this proof. Thanks for watching.